Okay.
Hi, everyone. For the next talk, I'll be presenting Boateng. Boateng is a PhD student at the University of Cincinnati. I, Michael Cantura, that just gave the previous talk, did graduate from University of Cincinnati, and where I worked with Boateng. And today, Boateng is going to present laser peening of additive manufactured Cobalt-Chromium-Molybdenum, which I started the research back when I was at University of Cincinnati. And Boateng and I worked under the supervision of Professor Vasudevan. And Boateng's PhD focuses around additive manufacturing and different aspects of it. Today, Boateng will be presenting the laser peening effect on the additive manufactured Cobalt-Chromium-Molybdenum. So, Boateng, the floor is yours.
All right. Good afternoon, everyone. Thank you for joining this session. As you already know, my name is Boateng Twum Donkor. I'm a PhD final year student at the University of Cincinnati. And this is actually Michael's Cantura's project, as he said, and I'm working with him on it. This project is titled The Effects of Laser Shock Peening Processing Parameters on the Microstructure, Residual Stress, and Fatigue Behavior of Additively Manufactured Cobalt-Chromium-Molybdenum Alloy. This work is supervised by Dr. Vijay Vasudevan and internally funded by the Ohio Center for Laser Shock Processing for Advanced Materials and Devices at UCA. So for the outline of this presentation, I'll start with a brief background of cobalt-chromium alloy and move on to talk about the LSP process in general, and I'll proceed to give an overview of the microstructure of the as manufactured cobalt-chromium samples we worked with, then proceed to talk about the effect of laser shock peening on the various process properties of this alloy, such as the hardness, the residual stress, the phase transformation, the tensile, and the fatigue properties. Then finish up with the conclusion and future work. So for cobalt-chromium alloy, it is a very important alloy that was discovered by Elwood Haynes in the early 1900s. In the early days, it was primarily used in the aerospace industry for various parts of the engine due to its very good properties. That's the high strength, very high superior wear resistance, and excellent corrosion resistance, even at elevated temperatures. It was later adopted in the biomedical industry due to its high wear resistance and biocompatibility. In the biomedical industry, it is usually used for prosthetic knee and dental implants. In general, for alloy compositions with less than 38% chromium, there are two phases in this alloy, which are the high temperature FCC phase and the low temperature HCP phase. The FCC phase has relatively lower strength but higher ductility, while the HCP phase has higher strength but lower ductility. Fast cooling this alloy after solutionizing at higher temperature, usually in the FCC region, retains the FCC phase. And therefore, isothermal aging of this structure transforms the FCC phase to the HCP phase. And this is usually done between 790 degrees Celsius. It is important to note that the addition of molybdenum shifts, as you can see here, shifts the phase equilibria, and thus introduces a third phase, the sigma phase, which is quite detrimental to the properties of this alloy. This is a schematic of the LSP process we use. This technique uses high energy laser beam that ablates a thin superficial layer, which is usually the tape, and this generates a plasma that is confined by the confining medium, that's the water, resulting in a shock wave that propagates into the material, creating compressive residual stresses. There are a number of parameters we can vary to produce different results. This is the setup we have in the lab at the University of Cincinnati. As I've already mentioned, the additive manufacturing SLM process generates tensile residual stresses that reduces fatigue life, whilst LSP introduces deep compressive stresses, which improves fatigue life and other properties. So the main goal of this project is to demonstrate the feasibility of LSP as an AM post-process technique, and also investigate the influence of different LSP process parameters on the various properties of the additive manufactured cobalt-chromium alloy. For this experiment, few LSP parameters were varied to understand their impact on enhancing the investigated properties. The different conditions used are presented in this table. There are 5 conditions we use. 4 conditions we use the infrared laser, 1 we use the green laser. Out of the 4, 2 conditions we use black tape, and 2 we use aluminum tape. Going back to the as manufactured SLM samples, the SE and BSE images show that in the radial direction, the grains are elongated in the direction of the AM build direction, whereas in the axial direction, the grains have no directional effects. SRD results also show that the sample has almost full SEC structure with some sigma faces at the grain boundaries and finely dispersed carbides at the grain and also in the grain and also at the grain boundaries. When we look at the TEM images of the as manufactured sample, it shows the matrix as FCC with, as you can see there, with very high dislocation density, which is typical of the EM process due to its fast cooling process. Also, the images show carbides are distributed mostly at the cell boundaries. Now explaining a bit about the sample preparation. The cylindrical blocks were sliced. This one were sliced into rectangular strips using the EDM. These samples were then polished, and after that, laser peened with the set conditions. The samples were then EDM cut to shape for the tensile and fatigue test based on the ASTM standard as shown in this figure. So the first thing we looked at after peening is the hardness. LSP is a mechanical treatment that does not produce or induce much cold work into the materials. As seen in the as in here, the surface hardness of the material increases somewhere between 10 and 20%, depending on the peening condition. Looking to the hardness through the bed profile shows maximum increase of dirt at the surface, then drops down as we go deeper into the material to reach the baseline hardness at around 500 to 600 microns. When it comes to laser shock peening, residual stresses are a key factor in the enhancing of the material properties, especially in fatigue. Compressive residual stresses counteract the applied tensile stresses, reducing the net stress experienced by the material, delaying crack initiation, also decreasing the crack propagation rates. So similar to the hardness depth profile, the residual stress profile has highest magnitudes near the surface and also decreases as we go through the depth to about 400 to 500 microns. There's also a difference between the conditions, which highlights the benefits of using different processing conditions compared to the other. For this particular cobalt-chromium alloy, as shown, the black tape gives slightly high residual stresses compared to the AL tape. Also, the green laser generates higher magnitude of compressive residual stress compared to the infrared. So we see here, this is the black tape, and this one is for the green laser. Also, additionally, an interesting finding of the laser peening on the Cobalt-Chromium-Molybdenum alloy can be seen here, where starting from the baseline material, which was usually made up of approximately 99% FCC and just about 1% HCP. After laser peening, there was a phase transformation as seen here. The different laser peening conditions cause strain-induced phase transformation, creating around 50% HCP phase at the surface. Usually, this is very detrimental to cobalt-chromium alloys during cold weather because crack nucleation and propagation along crack nucleation and propagation starts along the ATP phases. However, strain-induced martensitic transformation is very beneficial as it significantly increases the strength and wear resistance. Hence, controlling this particular phenomenon is very relevant in the development of more durable alloys. Looking into the depth of one of the samples using EBSD, the phase analysis shows that a fraction of the surface has transformed from FCC to ACP and into a shallow distance in the material. In addition, the CAM maps show the high magnitude of misorientation at the surface due to the plastic deformation from LSP, which coincide with the areas of the phase transformation. Moving on to the results of the tensile testing, you can see the increase in strength of the laser pin samples is very obvious here, but this comes at the cost or the expense of a drop in the ductility. This table summarizes the result of the tensile test showing LSP increases the yield strength of this alloy by around 15%. But that comes at a cost of reduction in the ductility. There's not much difference between the conditions. So finally, for fatigue testing, we use the Uniaxial tension fatigue test. We conducted this at the maximum stress of 980 megapascal, and the result shows the extent of fatigue life improvement due to laser pinning. The laser pinning samples, as you can see here, show an increase in fatigue life in the order of 10 to 15 times. That's compared to that of the AM or the ASBIOT sample. With the infrared the infrared with 2 layers of black tape condition having the highest fatigue length and fatigue life, sorry. So in conclusion, we say laser shock pinning converts this high tensile residual stresses that is created from the AM process to compressive stresses that protects the material against different type of metal failures. And also, the laser pin sample showed an increase in hardness of about 10 to 20% and a yield strength of about 15%. And also, more importantly, the fatigue life, the laser pinning improved the fatigue life by about 10 to 15 times. Moving forward, we would like to dive more into characterizing the near surface microstructural features. We want to look at the effect of LSP when we incorporate other techniques such as the HIP, the heat treatment, laser etching, and etc. Sorry, we would also, as I said, we also like to dive deep into it and characterize more and do a lot of studies on the strain-induced martensitic transformation I discussed earlier. Thank you for your attention. And I'm ready to answer any questions.
Thank you, Boateng. Very great talk. There is a couple of questions. And as Boateng explained, I did the laser peening part back when I was at the University of Cincinnati, so I might be answering a few of those questions. So the first question that we got was, why is there a fluctuation as increase and then decrease around the 1,000 microns level for the hardness measurements? So if you go back to the hardness testing, it showed a bit of fluctuation as you started going towards previous one. So can you explain why is there fluctuations in the measurements?
You mean this part?
Yeah.
This usually that we usually get fluctuations, but I don't think it's. I don't even know how to explain this, but I don't think it's any phenomenon per se. It's just the material fluctuations. What do you think, Michael?
Yeah, so it's as you can see, the error bars, they're uncertainty bars, that uncertainty from the measurements causing the fluctuation, rather than the laser peening itself.
Yeah.
The second question was what information we get from the CAM maps in the EBSD, how it is related to the LSP-induced modification. So when you showed the EBSD maps, what are you trying to say in these stories?
So here we're talking about a strain. The CAM map will show the amount of strain in the sample, and the LSP will input some amount of strain into the sample. So for over here, we can see there's a lot of strain, especially near the surface where we have the red. So if I compared this to the AM build, you would see more of blue without any much strain.